Hi, thanks for joining me today. I've got an interesting problem to do with sets and coprime numbers. We call a set S, which is a subset of the positive integers up to 2k plus 1, coprime friendly if there exists m and n in S such that the greatest common divisor of m and n is 1. So in other words, if m and n are 1. And so this is a two-part problem. Part 1 is we want to find a set S with cardinality or with size k and such that S is not coprime friendly. So S has k elements in, but it's not coprime friendly. And part 2, we want to prove that if S is at least k plus 1, or the size of S is at least k plus 1, then S is coprime friendly. Okay, so if you want to have a go at this two-part problem, pause the video now and give it a go for yourself, and I'm going to dive straight into a solution. Okay, so for part 1, we want to find a set S with size k such that S is not coprime friendly, and we kind of have a stare at this and we kind of think of an obvious choice for S, and that is if S equals the set with 2 in it, sorry, not 1 in it, 2 in it, 4 in it, 6 in it, 8 in it, and so on, all the way up to 2k. So all the even numbers that are in the set 1 up to 2k plus 1. And obviously this has size k. And clearly any two numbers in here are even, and therefore their greatest common divisor will be at least 2. They both will share the factor 2, and therefore their GCD will be at least 2, and therefore it cannot be 1, and therefore there cannot exist m and n in this set S, which is coprime. So this is pretty straightforward. So this is the solution for part 1 done. Now part 2 gets a bit more interesting, where we prove that if S has just one more element, so if S has size at least k plus 1, then it has to have 2 elements in it which are coprime. Okay, so now we're going to assume that S has size at least k plus 1, and in fact we only need to prove the case for when the size of S equals k plus 1, because if it has more elements in it, then that's fine. That's not really going to make our problem more difficult. But anyway, S has size at least k plus 1. Now we're going to kind of split this into two cases. Case 1 is a pretty easy case, and that is when 1 is in S. Because if 1 is in S, then we can just take 1 and any other element in S, let's just call it M, and the greatest common divisor between those has to be 1. Because the greatest common divisor between 1 and any positive integer is always going to be 1. And that kind of solves our problem. So if 1 is in S, we're good to go. We know we can find a coprime pair. So the set S will be coprime friendly. Now case 2 is what happens when 1 isn't in S. And now, well, then we know that S is just going to be a subset of this guy. Okay, well, how many elements are there? Well, there are 2k elements there. So let's suppose that S has k plus 1 elements. Because as I say, we only need to worry about this. So if S had k plus 2 elements, we could just look at a subset, call it S prime, which has k plus 1 elements, prove that there's a coprime pair in there, and therefore there must be a coprime pair in S. Okay, so S has size k plus 1. So let's call the smallest number in S, let's call it U1. Then that's going to be less than U2, which is going to be less than U3, and so on, all the way up to U k plus 1, which is going to be less than or equal to 2k plus 1, like so. And now here's where things get interesting. What if I consider the difference between the ui's? So this is from I equals 1 all the way up to k. Well, these are k different numbers, and I know that they've all got to be positive integers in fact, because no two elements in S are the same, because it's a set. And I also know what these add up to, or at least I can find an upper bound for what these add up to. If I call these maybe ti, if I look at the sum of ti from 1 to k of ti, just telescoping, this is going to be uk plus 1 minus u1. And now uk plus 1 minus u1, well, uk plus 1 is at most 2k plus 1, and u1 is at least 2, so this is going to be less than or equal to 2k minus 1. So that means all the ti's, which remember are positive integers, when I sum them up, I get less than or equal to 2k minus 1. And there's k terms here, and their sum is less than or equal to 2k minus 1. Therefore, by the pigeonhole principle, there exists some m such that t subscript m is less than or equal to 2k minus 1 over k. But now, remember ti has to be a positive integer for each value of I. And so tm is less than or equal to 2k minus 1 divided by k. But that number there is a number which is slightly smaller than 2. Depending on what k is, might be like 1.9 something or whatever. Because 2k divided by k is 2, but then we still have this minus 1 over k term. So it's going to be 2 minus 1 over k. And therefore, maybe I'll write it up here, tm is going to be equal to 1. But remember, Tm is this guy here, so um plus 1 minus equals 1. So in other words, plus 1 equals plus 1. But that just tells me that in my set S, I must have two numbers, or two elements, which are consecutive integers. And it's a very, very easy to prove fact that if you take any two consecutive positive integers, they must be coprime. So I can choose and plus 1, and the greatest common divisor of those two will have to be 1. And that proves case 2 when 1 is not in S. And that solves our problem. So part 1, we can just choose the set of even integers that are less than or equal to 2k, and for case and then to prove part 2, where S has size at least k plus 1, we can just split it into two cases based on whether or not 1 is in S. Anyway, that's enough of me talking. I hope you have enjoyed this quick problem, a nice little pigeonhole principle video for you. If you're new to the channel, please do consider subscribing, and if you have enjoyed this video, please do give it a like as well. I'd really appreciate that. It helps out the channel and lets me know that you really enjoy these sorts of videos. Anyway, I'm going to stop waffling now. Thank you for watching. I'll catch you in the next one. Have a great day.